For 70 years, our picture was wrong. The Milky Way is not just 100,000 light-years across. It is at least twice that size, possibly even larger. All this time, we have been living inside a galaxy far bigger than the one taught in classrooms, drawn in textbooks, and calculated in scientific papers. Only recently has new technology exposed the truth. And this discovery reshapes everything. How we measure the universe, when Andromeda will collide with us, and even the question of whether we are truly alone. If you want to see how scientists redefined the scale of our cosmic home, hit the like button and subscribe. This is the story of the greatest correction in modern astronomy. Prepare yourselves. We begin. Part 1. The discovery that rewrote our cosmic address. Everything you learned about the Milky Way galaxy is wrong. Not slightly inaccurate. Not outdated by a few years. Fundamentally, catastrophically wrong. For 7 decades, every astronomy textbook, every classroom poster, every documentary you trusted told you the Milky Way measures 100,000 light-years across. That number is not even close to reality. The truth? Our galaxy is twice that size, maybe more. We have been living inside a cosmic giant while thinking we occupied a medium-sized neighborhood. The mistake was not small. It was not a rounding error. Scientists were off by a factor of 2, and that changes absolutely everything. Think about what this means. Every measurement built on that old number now crumbles. Every calculation about when Andromeda will collide with us needs revision. Every estimate of how many stars exist, how many planets could harbor life, where our galaxy ends and space begins, all of it demands a complete rewrite. This is not like discovering a new planet or finding an unusual star. This is realizing the stage where every human story ever told is twice as large as we believed. The scale of this error is staggering, and the implications ripple through every corner of astronomy. How did this happen? How did thousands of brilliant scientists spend decades measuring, calculating, and mapping our home galaxy while missing half of it? The answer reveals something profound about the challenge of understanding where you live when you cannot step outside to look. We are trapped inside the very thing we are trying to measure. And that limitation led to the biggest correction in modern astronomy. But before we dive into how the mistake happened, let us be clear about what we know now. The Milky Way stretches approximately 200,000 light-years from edge to edge. Some measurements push it even farther. The visible disk, the part filled with bright stars and glowing gas clouds, extends far beyond where we thought it ended. And beyond that visible boundary lies something even more massive, an enormous halo of dark matter wrapping around everything. Invisible but undeniable, extending the galaxy's gravitational reach to distances that make the old measurements look like educated guesses from centuries past. New data. When technology finally caught up, the revolution began quietly. No dramatic announcement, no press conference declaring we got everything wrong. Instead, data started accumulating from multiple sources, each one hinting that something was off. The Gaia spacecraft, launched by the European Space Agency, began tracking the precise positions and movements of over 1 billion stars. That is, billion with a B. Never before had astronomers mapped so many stars with such incredible accuracy. Gaia measures stellar positions down to microseconds of arc, distances no human eye could ever distinguish. It tracks how stars move through space, their velocities, their trajectories, and when scientists analyzed this flood of data, patterns emerged that did not fit the old models. At the same time, the James Webb Space Telescope started sending back observations that shocked everyone. Webb sees in infrared, penetrating dust clouds that block visible light. It revealed regions of the galaxy we could never clearly observe before. Distant spiral arms, hidden star clusters, faint structures at the galaxy's edge. Each new image extended our map outward. Webb was not designed to revolutionize our understanding of the Milky Way. It was built to observe the distant universe, the first galaxies, the birth of stars, billions of light years away. But in mapping distant cosmos, it accidentally rewrote our understanding of home. Radio telescopes contributed their own revelations. These instruments detect hydrogen gas, the most abundant element in the universe. Hydrogen emits radio waves at a specific frequency, and radio telescopes can map these emissions across vast distances. When researchers used radio surveys to trace hydrogen clouds at the galaxy's fringes, they found gas extending far beyond the supposed edge. The galaxy did not stop where visible stars thinned out. It kept going. Hydrogen clouds orbited at distances that made no sense if the galaxy was only 100,000 light-years across. Either physics was broken or our measurements were wrong. Each technology revealed a different piece of the puzzle. Gaia showed stellar motions that required more mass than we thought existed. Webb revealed hidden structure in regions we assumed were empty. Radio telescopes mapped gas clouds orbiting at impossible distances. Individually, any one of these observations might be dismissed as an anomaly. Together, they formed an overwhelming case. The Milky Way is enormous, and we missed it because we were looking with the wrong tools, measuring the wrong things, making assumptions that seemed reasonable but were fundamentally flawed. But the real breakthrough came from an unexpected source: stellar streams. These are rivers of stars, remnants of smaller galaxies that the Milky Way devoured millions of years ago. When a small galaxy wanders too close to a larger one, gravity tears it apart. The stars do not vanish. They scatter into long trails, cosmic fossils marking ancient violence. Scientists had known about stellar streams for years, but they treated them as curiosities, interesting features but not particularly useful for measuring the galaxy. That changed when researchers realized these streams are the most honest rulers we have. The inside problem: measuring your house while standing in the basement. Imagine you are blindfolded and standing somewhere in the middle of Texas. Your job is to measure the entire state. You cannot remove the blindfold. You cannot use GPS or maps. You can only feel the ground beneath your feet and listen to sounds around you. How accurately could you determine Texas's boundaries? How would you know when you reached the edge? That is essentially what astronomers face when measuring the Milky Way. We sit on a rock orbiting an average star in an outer spiral arm, about 26,000 light-years from the galactic center. We cannot see the whole picture. We cannot step outside for perspective. Dust clouds block our view in almost every direction. The galactic center, where most of the mass concentrates, hides behind thick walls of gas and debris. If you look toward the constellation Sagittarius on a dark night, you see a bright band of stars. That is the galactic center, or rather, the tiny fraction we can see through all the interference. With optical telescopes, we observe maybe 10% of the galaxy clearly. The rest hides in infrared wavelengths, radio emissions, and absolute darkness. It is like trying to understand a city's layout by standing in a basement with tiny windows. You see pieces, fragments, but never the complete structure. Compare this to measuring Andromeda, our nearest large galactic neighbor. Andromeda sits 2.5 million light-years away. From that distance, we see the entire galaxy at once, edge to edge, top to bottom. every spiral arm visible in a single photograph. We can count star clusters, measure rotational velocity, track satellite galaxies orbiting around it. Measuring Andromeda is straightforward because we have the perspective outsiders always possess. Measuring the Milky Way is like asking someone to describe their own face without ever using a mirror and while standing inside a fog bank. Early astronomers had no choice but to work with what they could see. They used Cepheid variable stars, which pulse at predictable rates. The pulsation period tells you the star's actual brightness, and comparing that to how bright it appears gives you the distance. Brilliant technique, but limited. You can only use it for stars close enough to observe clearly. Beyond a certain distance, Cepheids become too faint to measure accurately. Astronomers also tracked globular clusters, ancient spherical collections of stars that orbit the galactic center. Map enough globular clusters, and you can estimate the galaxy's size, except globular clusters do not extend to the galaxy's true edge. They cluster in the inner halo, giving a biased sample of the overall structure. For decades, the methodology seemed solid. Astronomers looked outward in every direction, tracked the brightest stars they could find, and drew a boundary where star density dropped significantly. That boundary sat at roughly 100,000 light-years. Case closed. Textbooks printed. Models built. The problem was not that astronomers were careless or incompetent. The problem was they measured what they could see and assumed that represented the whole galaxy. They treated the visible disk as the complete structure, ignoring the possibility that enormous amounts of material might exist beyond their detection limits. It was a reasonable assumption based on the tools available. It was also completely wrong. Stellar streams, the cosmic crime scene evidence. Stellar streams sound like poetry, but they are actually evidence of violence frozen in time. Millions of years ago, small galaxies wandered too close to the Milky Way. Our gravity grabbed them, pulled them apart like taffy, and scattered their stars into long ribbons circling our galaxy. These streams are not small. Some stretch wider than the entire distance from Earth to the Sun. Others contain thousands of stars moving in perfect formation, like cosmic convoys that will orbit for billions of years before dispersing completely. We never paid much attention to stellar streams before. They seemed like background noise, faint and distant features that did not tell us much about the galaxy's structure. That changed when scientists realized these streams follow orbital paths determined by gravity. Every star in a stream moves based on the total mass pulling on it, visible and invisible combined. Measure the stream's path accurately, and you measure the gravitational field. No guesswork required. No assumptions about what you cannot see. Pure physics written in the motion of stars. The Sagittarius stream became famous first. This massive trail of stars wraps around the entire Milky Way multiple times, like ribbon on a present. When researchers traced this stream across the sky, they found it extending far beyond the old galactic boundary. The stream kept going and going, which could only mean one thing: the Milky Way's gravity kept going too. If the galaxy ended at 100,000 light-years, the stream would fly off into space. Instead, it stayed in orbit at distances approaching 150,000 light-years and beyond. The stream was telling us the galaxy is much larger than we thought, and we finally started listening. Then came the GD1 stream, a thin river of stars in the outer halo. This stream is particularly interesting because it is so narrow and well-defined. Researchers mapped its precise curve and found something impossible according to the old models. The stream bent in ways that required far more mass than the visible galaxy contained. Either the laws of physics were broken, or we were missing something massive? The answer, as always, turned out to be dark matter. That invisible material extending twice as far as the visible stars. The streams revealed dark matter like invisible ink under ultraviolet light. The gravitational pull shaping these stellar rivers came from material we cannot see, will never see, but can measure through its effects. But what came next was even stranger. Scientists found streams orbiting at distances we thought were intergalactic space, the supposedly empty voids between galaxies. Except those voids were not empty. These streams proved the Milky Way's influence reaches farther than anyone imagined. Our galaxy does not stop at the visible edge. It keeps pulling, keeps claiming territory, keeps exerting gravitational control over regions we assumed were beyond its reach. The orphan stream is particularly haunting. It orbits so far out that for years, scientists debated whether it even belonged to the Milky Way or to some other galaxy passing through the neighborhood. New measurements confirmed it. The stream is ours, which means the Milky Way extends at least that far. Each new stream discovery added thousands of light years to the galactic radius. 5,000 here, 10,000 there. The numbers climbed steadily. 120,000 light years, 150,000, 180,000. Stellar streams gave astronomers something they desperately needed: ground truth. You can debate where the edge of the visible disk sits. You can argue about where darkness becomes intergalactic space. But you cannot argue with a stream of stars orbiting in perfect formation at a specific distance. Their path is mathematical proof. Their orbit is the truth. And the truth kept pushing the boundary outward, farther than comfortable, farther than explainable with old models. 200,000 light years. The streams said so. The math said so. The observations said so. The question was no longer how big the Milky Way is. The question became how we missed it for so long, and what else we are missing right now. 200,000 light years, the number that changed everything. 200,000 light years. Let that sink in for a moment. Not 100,000, not 110,000. With a small correction, double the Milky Way measures, approximately. 200,000 light years from edge to edge, possibly more, depending on how you define the boundary. This is not a minor revision. This is a fundamental rewrite of our cosmic address. Every poster in every classroom showing a neat 100,000 light-year galaxy is obsolete. Every documentary animation is wrong. Every Wikipedia diagram you trusted shows a galaxy half its actual size. What does 200,000 light-years actually mean? The number is so enormous, it becomes meaningless without context. Light travels at 186,000 miles per second. In 1 year, that light covers about 6 trillion miles. Multiply that by 200,000. The Milky Way stretches approximately 1.2 billion trillion miles across. Still incomprehensible. Try this. If you could travel at the speed of light, the absolute cosmic speed limit, it would take you 200,000 years to cross the galaxy. When light, leaving one edge, finally reaches the other side, modern humans have evolved, built civilizations, collapsed, and evolved again multiple times over. The photons that left the far edge of the galaxy when Neanderthals walked the Earth are just now arriving at the other side. Put another way, if Earth was the size of a grain of sand, the Milky Way would stretch farther than the distance from Earth to Jupiter, actually, much farther. The scale breaks human intuition completely. We evolved to understand distances we can walk, miles we can travel in a day, maybe hundreds of miles with effort. Our brains never developed the capacity to truly grasp billions of trillions of anything. But that incomprehensible size matters to you right now, today, in ways that affect humanity's future. Doubling the galaxy's size means doubling the volume of space, and volume increases with the cube of the radius. If the galaxy is twice as wide, it contains 8 times more space. Not double, 8 times. That dramatically changes everything. 8 times more room for stars means hundreds of billions more stars than we thought. 8 times more volume means 8 times more potential planets. The old estimate suggested 200 billion stars in the Milky Way. The new estimate pushes toward 400 billion, maybe more. Every single one of those stars could have planets. Every planet could have moons. Every moon could have subsurface oceans. The number of potential homes for life just doubled at minimum. Think carefully about what that means. If life is rare, occurring in only 1 in a billion star systems, we just added 200 billion more chances. If intelligent life exists somewhere out there, we doubled the probability of finding it, or them finding us. The search for extraterrestrial intelligence just became twice as promising. The odds shifted in favor of cosmic companionship. We might not be alone, and a bigger galaxy makes that possibility significantly more likely. But the size increase also changes our survival timeline. The Andromeda galaxy is heading toward us at 70 miles per second. When galaxies collide, they do not crash like cars. They merge slowly over hundreds of millions of years. Stars pass between each other. Very few actually collide because the distances between stars are so vast. But the gravitational chaos reshapes everything. Scientists previously calculated the Andromeda collision would begin in about 4.5 billion years. A bigger Milky Way means a bigger gravitational reach. The galaxies will start affecting each other sooner, maybe in 4 billion years, possibly less. Your descendants, if humanity survives that long, will watch the night sky transform as 2 galactic giants slowly spiral together before merging into one massive elliptical galaxy. 200,000 light-years is not just a number in a textbook. It is the stage where every human story ever told took place. It is the cosmic neighborhood we call home. It is the hunting ground where we search for alien life. It is the gravitational basin that holds our solar system, our planet, our species. And we just realized this stage is twice as large as we believed. Everything built on the old measurement now needs revision. Every calculation demands updating. The Milky Way revealed its true size, and astronomy will never be quite the same. Part 2. Dark Matter's Invisible Empire. The dark matter halo, the invisible giant around us. You are staring at the Milky Way right now, or you think you are. What you actually see is the skeleton, the bright parts, the decoration. 90% of the galaxy is completely invisible. Dark matter is not a theory anymore, not a hypothesis waiting for confirmation. It is measured, mapped, and undeniable. We cannot see it directly, cannot touch it, cannot detect it with any telescope ever built. But we see its effects everywhere. Stars orbit too fast. Galaxies spin without flying apart. Light from distant objects bends around invisible mass. The evidence is overwhelming, and it just rewrote the size of our home. In the Milky Way, dark matter does not just add extra weight, it builds the entire structure. Imagine a skyscraper where you can only see the windows, not the steel frame holding them up. That is our galaxy. The stars are windows glowing in the night. Dark matter is the frame, invisible but essential, without which everything would collapse. Scientists estimate dark matter outweighs visible matter by a ratio of about 10 to 1. For every star you see shining in the night sky, there is 10 times more invisible mass nearby. This material forms a massive halo around the galaxy, spherical and diffuse, stretching far beyond the visible disk. The old measurements ignored this halo almost completely. Astronomers focused on what they could see: the bright spiral arms, the glowing core, the obvious features that showed up in photographs. The galaxy appeared to be 100,000 light-years across, because that is where visible stars thinned out to almost nothing. But dark matter keeps going. It extends twice as far, maybe 3 times, possibly more. Think of it like an iceberg floating in the ocean. You see the tip above water, maybe 1/10 of the total mass. That is the visible galaxy. Below the surface, hidden from sight, sits a mountain of ice 10 times larger. That is the dark matter halo. The true size includes both parts, and we spent decades measuring only the tip. Researchers map this invisible halo using a technique called gravitational lensing. When light from a distant galaxy passes near the Milky Way, our dark matter bends it slightly, just as Einstein predicted. The amount of bending reveals the amount of mass. Measure the bending carefully, calculate the distribution, and you map the invisible. The results shocked everyone. Our dark matter halo extends out to nearly 250,000 light-years in the dense regions. Some models suggest the faint outer regions reach 400,000 light-years, maybe farther. The galaxy is not a disk of stars floating in empty space. It is an enormous ball of dark matter, with stars sprinkled through the center like decorative lights. But here is the twist that keeps astronomers arguing at conferences. Where exactly does the Milky Way end and intergalactic space begin? Is it where the dark matter density drops to half its peak value, a quarter, 1/10? There is no official boundary, no cosmic border wall, just a gradual fading into nothing. For practical purposes, scientists use something called the virial radius. This marks the point where material is gravitationally bound to the galaxy. Inside this radius, everything orbits together as one system. Outside, space is truly empty, or as empty as space ever gets. For the Milky Way, the virial radius sits around 200,000 to 250,000 light-years. Double the old estimate, all because of invisible mass we cannot see but cannot ignore. Mass explosion. From 1.5 trillion to 4 trillion suns. Mass. Everything in the universe comes down to mass. Gravity depends on it. Orbits require it. Structure forms because of it. And the Milky Way just gained an enormous amount of weight. Trillions upon trillions of solar masses that appeared in the data like cosmic accounting errors, except they were not errors. The mass was always there. We just could not measure it correctly. The old estimate said our galaxy contained about 1.5 trillion times the sun's mass. Most of that was dark matter, with visible stars and gas making up maybe 10%. The new measurements, for trillion solar masses, possibly more. We nearly tripled the mass estimate in less than a decade. What does a solar mass actually mean? Our sun weighs about 2 billion kilograms. That number is so absurdly large it becomes meaningless. One solar mass is simply the sun's weight, used as a convenient unit. For comparison, Earth weighs about 330,000 times less than the Sun. Jupiter, the largest planet in our solar system, weighs about 1,000 times less. Everything in our solar system, except the Sun, adds up to barely 1% of one solar mass. Now multiply the Sun's mass by 4 trillion. That is the Milky Way, a gravitational colossus. Where did all this extra mass come from? Did the galaxy suddenly gain weight overnight? Did material appear from nothing like magic? Obviously not. The mass was always there, exerting gravity, shaping orbits, holding the galaxy together. We just could not measure it accurately. Most of the extra mass is dark matter, that mysterious substance that only interacts through gravity. The old measurements focused on visible stars and glowing gas clouds. They estimated dark matter indirectly using galactic rotation curves, measuring how fast stars orbit the center. The faster they orbit, the more mass must be present. Simple physics, elegant mathematics, completely wrong results. The mistake came from sampling bias. Those rotation measurements only covered the inner galaxy, the region where stars are common and observations are relatively easy. Nobody accurately measured the outer halo where dark matter dominates and stars are sparse. That outer region contains enormous amounts of mass, but it remained invisible to our calculations. New techniques changed everything. Satellite galaxy orbits provided direct mass measurements at huge distances. If a small galaxy orbits at a specific distance and speed, you can calculate exactly how much mass holds it in place. No assumptions required. Pure Newtonian mechanics. Stellar streams mapped the gravitational field in the outer regions, revealing dark matter concentrations we never knew existed. Computer simulations compared our galaxy to thousands of virtual galaxies with known masses, helping calibrate the measurements. All the methods agreed within reasonable margins for trillion solar masses, possibly more. The Milky Way is a heavyweight, and we spent decades thinking it was a middleweight. This discovery has enormous implications that ripple through every branch of astronomy. More mass means stronger gravity, and stronger gravity means we dominate our local neighborhood more completely than anyone realized. We can hold more satellite galaxies in orbit. We can strip stars from passing neighbors more easily. We command the local group like a gravitational emperor. Andromeda was always considered the bigger sibling, the alpha galaxy in our cosmic neighborhood. But new measurements suggest we might be equals, or possibly even larger. The Milky Way and Andromeda Way, roughly the same. 4 trillion solar masses each. 2 galactic superpowers on an inevitable collision course. Neither one clearly dominant, both massive enough to reshape everything they touch. More mass also changes how we understand our formation history. Galaxies grow by eating smaller galaxies in a process astronomers politely call hierarchical assembly. The bigger you are, the more you have consumed over cosmic history. A 4 trillion solar mass galaxy has a violent past. We devoured hundreds of dwarf galaxies, possibly thousands. Every stellar stream in the halo is evidence of a meal, a galaxy that wandered too close and paid the ultimate price. The Sagittarius dwarf is being eaten right now, torn apart in real time. In a few 100 million years, no trace of it will remain except ghosts in the data. Scattered stars that once belonged to something else. But here is the part that should make you pause and think. If we are 4 trillion solar masses, and most of that is dark matter, we live in a galaxy made mostly of invisible material. 90% of everything around us is something we cannot see, cannot touch, cannot directly detect. You think you know where you live. You think you understand your cosmic neighborhood. You are swimming in an ocean of dark matter and you cannot feel the water. For trillion solar masses of mostly invisible material surround you right now, holding your solar system in orbit, shaping the galaxy's structure, building the scaffolding on which everything visible rests. That is home. That is the Milky Way. And we just realized how enormous and how strange it truly is. Satellite galaxies, the cosmic prisoners in our orbit. The Milky Way is not alone in space. Dozens of smaller galaxies orbit around us, like moons around a planet, trapped by our gravity, doomed to eventual destruction. We call them satellite galaxies, and they just rewrote our cosmic address by revealing how far our gravitational influence actually reaches. The Large Magellanic Cloud is the biggest, visible from the southern hemisphere as a cloudy smudge in the night sky. It contains about 30 billion stars, which sounds enormous until you realize the Milky Way has more than 10 times that number. The Small Magellanic Cloud sits nearby with 7 billion more stars. Then come the dwarf galaxies: Sagittarius Dwarf, Draco Dwarf, Ursa Minor Dwarf, each one a miniature galaxy with its own stars, its own history, its own doomed orbit. For years, scientists treated these satellites as neighbors, separate objects passing by in the cosmic neighborhood. But new measurements revealed an uncomfortable truth. They are not passing by. They are trapped, gravitationally bound, orbiting within the Milky Way sphere of influence, with no hope of escape. This discovery changed everything about how we measure the galaxy. When you measure how fast a satellite orbits, you can calculate the mass holding it in place. More mass means tighter orbits at closer distances. Less mass means objects drift away over time. The satellite galaxies orbit at specific distances and speeds that reveal our total gravitational pull. Visible and invisible combined, the Large Magellanic Cloud sits about 160,000 light-years away from us. It orbits the Milky Way once every 1.5 billion years. A glacially slow waltz by human standards, but rapid by cosmic timescales. For it to maintain that orbit at that distance, our galaxy must be massive. Far more massive than the old estimates suggested. The math is straightforward. Plug in the distance, plug in the orbital period, calculate the mass required. 4 trillion solar masses. The satellites were screaming the truth at us for decades, and we finally started listening. Researchers tracked dozens of satellites and found the same pattern everywhere. They all orbit farther out than expected based on old models. They all move faster than predicted. The only explanation that fits the data. The Milky Way is bigger and heavier than we realized. But the real breakthrough came from tidal streams. The long trails of stars ripped from satellite galaxies as they orbit too close to us. When a satellite galaxy passes through our outer halo, the Milky Way's gravity pulls harder on the near side than the far side. This tidal force tears the galaxy apart, stretching it like cosmic taffy. Stars get pulled away in long ribbons that wrap around the entire galaxy. The Sagittarius Dwarf is currently being destroyed this way, ripped apart in slow motion over hundreds of millions of years. Its stars stretch across the sky in a stream visible to modern telescopes, wrapping around the entire Milky Way multiple times. These tidal tails act as test masses, revealing where the gravitational field is strongest, where it weakens, where the true boundary sits. Map enough tidal streams, and you map the edge of the galaxy with mathematical precision. What scientists found shocked them completely. The streams extended far beyond the supposed galactic edge. Some reached out past 150,000 light-years, others hit 200,000. A few hints suggested material even farther out. The satellites were providing undeniable proof. The Milky Way is huge, and its gravitational reach extends far beyond the visible stars. This had immediate implications for understanding the local group of galaxies. If our galaxy is this large, the space between us and Andromeda is smaller than we thought. The gravitational influence of each galaxy reaches farther into what we assumed was neutral territory. Collisions happen sooner. Mergers start earlier. Territory that seemed like empty intergalactic space actually belongs to one galaxy or another. Every satellite galaxy became a data point in the calculation. Every orbit provided a measurement tool. Together they painted a picture of a galactic giant, not the medium-sized spiral we imagined ourselves to be. And here is the haunting part that keeps astronomers searching. Some satellites orbit so far out we are still discovering them. Every few years, astronomers find another dwarf galaxy hiding in the data, lurking in the outer halo. Each new discovery extends our boundary a little farther, adds a little more mass to the total. How many more are out there waiting to be found? How much bigger does the Milky Way actually get? The satellites hold the answers, orbiting in darkness, waiting for us to notice them and add them to the census of our cosmic empire. The rotation curve anomaly, stars moving too fast. The galaxy is spinning too fast. It should fly apart. Stars at the outer edge orbit at speeds that make absolutely no sense according to basic physics. They should escape into intergalactic space like marbles flung from a spinning plate. They should obey Kepler's laws of motion, the same laws that govern planetary orbits. They should slow down as you move away from the center, just like planets do in our solar system. They do not. And for decades, nobody fully understood why. Here is the problem, clear and undeniable. In our solar system, planets farther from the sun orbit slower. Mercury races around in 88 days. Earth takes 365 days. Neptune takes 165 years. The farther out you go, the weaker the sun's gravity, the slower the orbit. This is fundamental physics that Isaac Newton figured out more than 300 years ago. Galaxies should work exactly the same way. Most of the visible mass concentrates near the center in a bright bulge of old stars. Stars farther out should feel weaker gravity. Their orbital speeds should decrease with distance, creating a nice smooth curve dropping off at the edges. Except that is not what happens in the real universe. When astronomers measure the orbital speeds of stars at the edge of the Milky Way, they find something impossible. Stars at the edge orbit at nearly the same speed as stars much closer in. The rotation curve stays flat instead of dropping off. This defies everything we know about gravity and orbital mechanics. It is like watching Neptune orbit the Sun as fast as Mercury. It should not happen. It cannot happen. Unless there is more mass out there than we can see. Invisible mass, providing extra gravity to keep those outer stars moving fast. Dark matter. Always dark matter. The invisible halo provides the extra mass needed to explain the flat rotation curve. It extends far beyond the visible stars, keeping outer objects moving fast enough to stay in orbit. The flat rotation curve is the smoking gun, the proof that dark matter exists in huge quantities throughout the galaxy. But even accounting for dark matter, some mysteries remain. Even with our updated mass estimates, some stars in the outer halo move at surprisingly high velocities. Some reach 130 miles per second, others hit 150. These velocities put them barely below escape velocity, the minimum speed needed to leave the galaxy entirely. Why do they orbit so close to the edge of escape? What fine-tuned mechanism keeps them bound but barely? This is called the escape velocity problem, and it haunts astronomers who study galactic dynamics. One possibility is that we still underestimate the galaxy's mass, even with the new measurements. Maybe there is even more dark matter than current models suggest. Maybe the halo is denser at the edges than we think. Maybe our mass calculations are still wrong, just less wrong than before. Another possibility involves recent galactic growth. If the Milky Way devoured a large dwarf galaxy in the past few billion years, that merger could have injected stars into fast orbits. These stars have not had enough time to settle into stable circular paths. They still carry the energy from the collision, moving at speeds that reflect their violent origin. Evidence supports this idea. We know the Milky Way ate Enceladus about 10 billion years ago and is currently digesting Sagittarius. Each merger adds stars with unusual velocities to the mix. But what comes next is even stranger and highlights how much we still do not understand. Some stars move too slow, not too fast. These are like hypervelocity stars in reverse. Objects that should orbit faster based on their location but drift along like they are trapped in cosmic molasses. Nobody has a satisfactory explanation for these slow movers either. They exist in the data, undeniable and unexplained, mocking our understanding of galactic dynamics. The rotation curve should be simple. Measure speeds at different distances, calculate the mass distribution. Everything fits together nicely. Instead, every new measurement reveals more anomalies, more outliers, more stars doing things they should not be able to do according to standard models. This is where different dark matter theories get tested against reality. Warm dark matter produces smoother velocity profiles. Cold dark matter creates lumpier structures with more variation. Self-interacting dark matter behaves differently in galactic cores compared to the outer regions. So far, cold dark matter fits the observations best, but the fit is not perfect. Discrepancies remain. Small ones, nagging ones. The kind that might point toward new physics, or might just be measurement errors we have not eliminated yet. The galaxy spins faster than simple models predict. Stars orbit at speeds that defy easy explanations. And the larger galactic size makes the problem worse, not better. More volume means more stars with unusual velocities to explain. More space means more opportunities for weird dynamics to emerge. Physics works everywhere else in the universe. It works perfectly in solar systems, in star clusters, in distant galaxies. But here, in our own cosmic backyard, in the Milky Way's rotation curve, something is still not quite adding up. And that should make you wonder what other surprises are hiding in the data, waiting to be discovered. The virial radius. Where does our galaxy actually end? Draw a line marking the edge of the Milky Way. Sounds simple enough. It is actually impossible. Galaxies do not have boundaries like countries on a map or continents on a globe. No border wall. No sign saying now leaving the Milky Way. Stars just thin out gradually, slowly, smoothly, until there are almost none. Or maybe a few scattered stragglers. Where exactly does that transition point sit? When does galaxy become not galaxy? This is not a philosophical question. It is a practical problem that affects every measurement we make. Astronomers need a definition, a standard measurement, a way to compare galaxies consistently. But nature refuses to cooperate. The universe does not care about our need for clean categories and neat boundaries. Several definitions exist, and none of them are perfect. The optical radius marks where visible stars become too faint to detect with current telescopes. This gives you the bright disk, the obvious part. Roughly 100,000 light-years for the Milky Way using old measurements. But this definition ignores all the faint stars, dim dwarfs, and scattered halo objects. It is like measuring a city by counting only skyscrapers and ignoring all the houses, parks, and suburbs. The virial radius is more scientific and more widely used in professional astronomy. It marks the boundary where objects are gravitationally bound to the galaxy. Inside this radius, stars and gas orbit the galactic center as part of one cohesive system. Outside this radius, objects drift independently through space. For the Milky Way, this gives about 200,000 to 250,000 light-years, depending on the exact model used. Much better than just measuring visible light, but even this definition has problems that become obvious when you think about it carefully. Some stars outside the virial radius still move with the galaxy through space. They share our motion relative to other galaxies. They formed here billions of years ago. Are they part of the Milky Way or not? The virial radius says no. They are too far out and not gravitationally bound. Common sense says maybe they came from here and still associate with the galaxy. Neither answer is completely satisfying. Then there is the dark matter halo, which extends far beyond everything else. If the halo reaches 400,000 light-years out, or even farther, is that the real edge? Most astronomers say no. The halo fades so gradually that choosing any specific boundary becomes arbitrary. It is like trying to mark where Earth's atmosphere ends. Technically, atmospheric particles exist thousands of miles above the surface, getting thinner and thinner until they blend into the solar wind. Practically, the atmosphere is gone after about 60 miles up. Where do you draw the definitive line? Different fields of study use different definitions because they care about different things. The same problem applies to galaxies. The situation gets even more complicated when you consider galactic winds and outflows. The Milky Way produces massive jets of gas blown outward by supernova explosions and stellar winds. This material travels hundreds of thousands of light-years out into space. Is that gas still part of the galaxy, or has it become intergalactic medium? Some of it will fall back eventually. Gravity pulls it down over millions of years. The galaxy recycles its gas in a process astronomers call the baryon cycle. But some gas escapes forever, lost to the void. At what point does Milky Way gas stop being ours and become someone else's problem? The Magellanic Stream adds another layer of confusion. The large and small Magellanic Clouds leak gas as they orbit us. This gas forms a stream stretching across a huge portion of the sky. Is that stream part of the Magellanic Clouds, part of the Milky Way, or neither? All three answers have defenders in the scientific literature. Andromeda poses the same problem from the other direction. Its dark matter halo might already be touching ours. When two halos overlap and interpenetrate, where does one galaxy end and the other begin? The space between becomes shared territory, disputed, co-owned by both galaxies. This is not just academic hair-splitting. The definition you choose affects mass estimates, size comparisons, and our understanding of when the Andromeda collision truly begins. If the halos are already merging in their outer regions, the collision started millions of years ago. We are living inside it right now. Most astronomers settle on practical working definitions that serve specific purposes. The disk ends where active star formation stops. The stellar halo ends at the virial radius. The dark matter extends as far as simulations suggest based on galaxy formation models. Each definition serves different research needs. None of them perfectly captures the messy reality of what a galaxy actually is. Here is the uncomfortable truth that textbooks rarely admit. The Milky Way is not an object with clear boundaries. It is a region of space, a zone of gravitational influence, a neighborhood with a dense center and fuzzy edges that fade into something else. 200,000 light-years is our current best answer for the virial radius. But ask that same question again in 10 years after better surveys and more data. The number will probably change. It always does. The uncertainty will shrink as measurements improve. Confidence intervals will tighten, but the number will never be perfect, never final, never complete. Just progressively better approximations of a boundary that does not really exist. We live in a galaxy without edges, in a universe without borders. Everything blends together, everything connects, and we are still learning to measure a cosmos that refuses to be measured the way we want it to be. Part 3. Collision Course with Andromeda. The collision timeline earlier than we thought. Andromeda is coming. This is not speculation or theory. This is confirmed observational fact. Our neighboring galaxy is racing toward us at 70 miles per second, closing the distance with every passing moment. The collision is inevitable, unavoidable, written in the mathematics of gravity. For decades, scientists calculated the impact would happen in approximately 4.5 billion years. Mark your calendars. Except those calculations assumed the old galactic sizes. The measurements we now know were completely wrong. Smaller Milky Way, smaller gravitational reach, more empty space between us and Andromeda. A bigger Milky Way changes everything about that timeline. Gravity reaches farther when you have more mass. The physics is straightforward. Our 4 trillion solar mass galaxy exerts gravitational influence far beyond the visible stars. Andromeda, weighing roughly the same, does exactly the same thing. Their massive dark matter halos stretch hundreds of thousands of light-years outward into space. When those halos touch, when their gravitational fields begin to overlap and interact, the collision begins. Not when the visible disks merge, not when stars start passing through each other. When the invisible halos make first contact. And that might happen much sooner than anyone expected. Think of 2 people walking toward each other across a room. If they are both larger than you initially thought, they bump into each other sooner. Same principle, just scaled up to galactic proportions. New models, incorporating the updated sizes, suggest the interaction could begin in under 4 billion years, maybe 3.5 billion. The exact timeline depends on precise measurements astronomers are still collecting. Tracking velocities with incredible accuracy, mapping dark matter distributions, refining computer simulations, but the trend is absolutely clear. Bigger galaxies mean earlier contact. The show starts sooner than we thought. Here is what happens during a galactic collision, step by catastrophic step. First, the outer dark matter halos start merging. This phase is completely invisible to any telescope. Dark matter does not emit light, does not absorb light, does not interact with anything except through gravity, but that gravitational interaction is real, measurable, and incredibly powerful. Stars throughout both galaxies feel the pull from 2 galactic centers instead of one. Orbits destabilize. Some stars get flung into intergalactic space at incredible velocities, ejected forever. Others plunge toward one of the cores, their paths warped beyond recognition. Then the visible disks collide. Not a crash in the traditional sense, more like 2 clouds of fireflies passing through each other. Stars are so fantastically far apart that direct collisions are incredibly rare. You could fit millions of Earths between neighboring stars. The distances are so vast that stars pass by each other like ghosts, never actually touching. But the gravitational chaos is absolutely real and utterly destructive to galactic structure. Star formation explodes across both galaxies as gas clouds compress and collapse. New stars ignite by the millions, creating a cosmic fireworks display visible across the universe. The Milky Way and Andromeda will orbit each other multiple times after first contact, dancing around each other, spiraling closer with each pass. Each passage strips away more material. Tidal forces shred the elegant spiral arms we see today. Stellar streams scatter in every direction like cosmic debris. The once beautiful structures become warped, distorted, completely unrecognizable. Eventually, maybe 1 billion years after first contact, the galaxies merge completely into one. The result is a massive elliptical galaxy with no spiral arms, no organized disk. Just an enormous blob of roughly 800 billion stars orbiting in random directions. Astronomers already named this future galaxy Milkomeda, a cute name for the death of two ancient spirals and the birth of something entirely new. Dark matter halos touching. The invisible collision already began. Here is the part that should make you pause and reconsider everything. The dark matter halos might already be touching right now. Not will touch in billions of years. Might be touching already. Andromeda sits 2.5 million light-years away when you measure the distance between the visible centers. That seems like an enormous gap, a vast empty gulf separating two island galaxies. But dark matter halos do not respect those comfortable distances. Our halo extends at least 250,000 light-years out from the center, possibly much farther. Andromeda's halo does the same, maybe even larger, given that Andromeda might be slightly more massive than us. Subtract those halos from the total distance. 2.5 million minus 500,000 leaves 2 million light-years of truly neutral space between the dense regions. But if the halos extend farther than conservative estimates suggest, if they reach 400,000 or 600,000 light-years out, the math changes dramatically. Suddenly, you are looking at much less separation. And if the very outermost tendrils of dark matter extend even farther, to the absolute limits of gravitational binding, those halos could already be two invisible clouds of mysterious particles mixing together in the space between galaxies, completely undetectable by any instrument we possess. Think about what that means for a moment. The collision everyone talks about as a future event might have already begun. The opening act of a billion-year cosmic drama might be playing out right now in complete darkness. Invisible to every telescope ever built, we cannot see dark matter directly. We can only infer its presence through gravitational effects. So how would we even know if the halos are touching? What signature would that leave in our observations? The answer is subtle and complex. We would see unusual velocities in satellite galaxies orbiting between the two large spirals. We would detect streams of stars with unexpected motions. We would find objects gravitationally disturbed by poles from both galaxies simultaneously. Some researchers think they are already seeing these signatures in the data. Dwarf galaxies in the space between us and Andromeda show peculiar velocities that do not quite fit models assuming two separate, isolated galaxies. Several stellar streams have trajectories that suggest multiple gravitational influences pulling in different directions. The evidence is not conclusive, not yet, but it is suggestive, enough to make astronomers wonder if the invisible merger has already commenced while we watch the visible portions of both galaxies, blissfully unaware of the gravitational dance happening in the darkness between them. The implications are profound and unsettling. If the collision began already, we are not waiting for a future catastrophe. We are living inside one. The gravitational chaos has started. The destabilization of orbits has commenced. Every star in both galaxies, including our Sun, is already feeling subtle effects from the approaching merger. Not enough to notice in a human lifetime or even in a million human lifetimes, but measurable over tens of millions of years. Our solar system's orbit around the galactic center is already being perturbed, pulled slightly off its normal path by Andromeda's distant but growing influence. Collision physics, how giant galaxies destroy each other. Scale changes everything in galactic collisions. When two small dwarf galaxies merge, the interaction is relatively quick, finished in a few 100 million years. They collide, mix, settle into a new equilibrium, done. But when two massive galaxies like the Milky Way and Andromeda collide, the process takes much longer and becomes far more complex. The increased mass means stronger gravity, and stronger gravity means interactions continue over billions of years. Each galaxy has enough gravitational energy to disrupt the other completely while simultaneously being disrupted itself. It is mutual destruction playing out in ultra-slow motion. Here is what happens in detail as giant galaxies collide. First contact occurs when the dark matter halos into the halos are so diffused they pass through each other like fog banks, mixing together. Dark matter particles do not collide physically because they almost never interact with anything. They simply occupy the same space simultaneously, their only interaction being gravitational. But that gravitational interaction is enough to start pulling stars in both galaxies off their normal orbits. Objects that spent billions of years in stable paths suddenly feel forces from unexpected directions. Next, the outer stellar halos interact. Stars in these regions are already moving fast, many of them barely gravitationally bound to their home galaxies. When another massive object approaches, some stars gain just enough extra velocity to escape completely, flung into intergalactic space at hundreds of miles per second. They become rogue wanderers, destined to drift alone through cosmic voids for trillions of years. Others get captured by the approaching galaxy, stolen like prisoners of war. The galaxies start exchanging stars and gas long before their main bodies collide. Then come the devastating tidal forces. As the galaxies pass close to each other, gravity pulls harder on the near side than the far side. This difference in gravitational pull stretches both galaxies like taffy. Material gets pulled into long streamers called tidal tails, extending millions of light years into space. These tails are hauntingly beautiful when seen in photographs of other colliding galaxies. Long arcs of stars and gas curving away from the collision site. Temporary structures that will eventually disperse, but which mark the violence that created them. The visible disks collide last in the sequence. When two galactic disks finally interpenetrate, something remarkable and counterintuitive happens. Despite containing hundreds of billions of stars, actual stellar collisions remain incredibly rare. The stars are just too far apart, but gas clouds in both galaxies compress violently when they meet. Compressed gas collapses under its own gravity. Collapsed gas forms new stars. Star formation explodes across both galaxies in what astronomers call a starburst event. Millions of massive young stars ignite simultaneously, burning blue-white and incredibly bright, making the merged system visible across half the universe. But here is where size matters most and changes outcomes dramatically. Bigger galaxies have deeper gravitational wells, steeper gravitational slopes that make escape much harder. When material gets pulled into tidal tails during collision, much of it eventually falls back in larger systems. Smaller galaxies lose material permanently to the void. Larger galaxies like ours and Andromeda will recycle most of it. The merger timeline stretches longer with increasing mass. Small galaxies might complete their merger in 1 or 2 close passes. Large galaxies orbit each other 3, 4, maybe 5 times. Each orbit strips away more material and drives the cores closer together until finally friction from gas and gravitational interactions drain enough orbital energy. The galaxies spiral inward for the final merge. Milkomeda, the birth of a monster galaxy. The final product of our collision with Andromeda already has a name. Astronomers call it Milkomeda, a combination of both parent galaxies, and it will be enormous. 800 billion stars, 4 trillion solar masses from each galaxy combining into one massive system. The numbers become almost meaningless at this scale. 800 billion stars means 800 billion potential solar systems, hundreds of trillions of planets, more worlds than human minds can comprehend. Milkomeda will be one of the largest galaxies in the local group, a true heavyweight dominating everything around it. But Milkomeda will not look like either of its parent galaxies. The beautiful spiral structures we see today in both the Milky Way and Andromeda will be completely destroyed. Spiral arms require organized rotation, all the stars orbiting in roughly the same plane and direction. Galactic collisions scramble those orbits beyond recovery. Stars end up moving in every possible direction, random trajectories with no overall pattern. The result is an elliptical galaxy, essentially a 3-dimensional blob with no distinct features. Just an enormous swarm of stars orbiting a common center in chaotic paths. The collision will also trigger other dramatic events. Both the Milky Way and Andromeda have supermassive black holes at their centers. Ours weighs about 4 million times the Sun's mass. Andromeda's is much larger, roughly 100 million solar masses. When the galaxies merge completely, those black holes will eventually spiral toward each other and merge into one titanic black hole, weighing over 100 million solar masses. This merger will release gravitational waves powerful enough to be detected by future instruments across the observable universe. The ripples in space-time itself propagating outward at light speed, carrying the signature of 2 black holes becoming one. Star formation will spike dramatically during the collision, then crash completely. The initial starburst will consume most of the available gas in both galaxies over a few 100 million years. After that fuel runs out, star formation stops almost entirely. Milkomeda will become what astronomers call red and dead, a galaxy filled with old reddish stars, slowly fading, with no new stellar generation to replace the ones that die. Over trillions of years, the galaxy will grow dimmer and dimmer as its stars exhaust their fuel and fade away one by one. Earth's fate: will we survive the cosmic catastrophe? Here is the question everyone wants answered. Will Earth survive the collision? Will the Sun survive? Will humanity be around to witness this cosmic catastrophe? The answers are complicated and depend on many factors we cannot predict with certainty. Good news first. The Sun will likely survive the merger. Our solar system sits about 26,000 light-years from the galactic center, far enough from the most violent regions that we will probably avoid the worst gravitational chaos. Direct collision with another star remains almost impossibly rare. Space is just too empty. Earth might get flung into a different orbit, possibly ejected entirely into intergalactic space, or it might stay roughly where it is. The odds slightly favor survival in some form. Bad news: the Sun will be long dead by the time Milkomeda fully forms. Our star has about 5 billion years of hydrogen fuel remaining. It will swell into a red giant, engulf the inner planets including Earth, then collapse into a white dwarf. This happens before the Milky Way and Andromeda complete their merger. Earth as we know it will be gone. But humanity might witness the early stages if our species survives that long. The first close passes between galaxies could happen in 3.5 to 4 billion years. The sun will still be shining then, though hotter and brighter than today. If humans or our descendants are still around, they will watch the night sky transform in ways hard to imagine. Andromeda will grow larger and brighter over millions of years, eventually filling half the visible sky. A second galactic disk hanging above us, close enough to resolve individual bright stars and nebulae. Then the galaxies will dance around each other in a cosmic ballet visible to the naked eye. Spiral arms distorting, tidal tails forming, new stars igniting by the millions. The night sky will become a constantly changing display of galactic destruction and rebirth. A bigger Milky Way moved up that timeline. The collision starts sooner because our gravitational influence reaches farther. The early stages begin earlier. The chaos arrives faster. And here is the part nobody talks about enough. What if Andromeda is also bigger than we measured? Their estimates could be just as wrong as ours were. If both galaxies are significantly more massive than old measurements suggested, the collision happens even sooner than current models predict. The gravitational chaos becomes more intense. The tidal disruption reaches farther. Everything accelerates. 4 billion years sounds like forever, an incomprehensibly distant future. But on cosmic timescales, it is tomorrow. Tomorrow just got a little closer. The clock is ticking. Andromeda approaches, and our newly discovered size means we will feel its gravitational embrace sooner than anyone expected just a decade ago. Part 4: Galactic Cannibalism and Our Violent Past. Sagittarius Dwarf. A galaxy being eaten alive right now. The Milky Way is a cannibal. Our galaxy grew to its current size by eating others, consuming hundreds of smaller galaxies over billions of years. Their stars became ours through gravitational theft. This is not ancient history. It is happening right now. The Sagittarius Dwarf galaxy is being torn apart as you read this, devoured in real time. This dwarf contains about 400 million stars, orbiting too close to escape our gravitational grip. Over the next billion years, those stars will scatter across the Milky Way like seeds in the wind. In 2 billion years, no trace of Sagittarius will remain except ghosts in astronomical data. Watch closely and you can see the destruction unfolding. The dwarf's stars stretch into a long stream wrapping around our entire galaxy, multiple times like ribbon on a cosmic present. This stream is evidence of violence, proof that gravity tears galaxies apart without mercy. Each orbit pulls more stars away from the core. Each pass weakens the dwarf's structure until nothing coherent remains. This is how galaxies grow in the universe, not through slow, peaceful accumulation. Through violence, conquest, and cannibalism. The strong dominate. The weak become meals. Enceladus, the ghost of a galaxy we destroyed. Sagittarius is just the latest victim in a long history of galactic murder. About 10 billion years ago, the Milky Way collided with a substantial galaxy called Enceladus. This was not a minor dwarf. This was a real galaxy containing billions of stars, perhaps 1/4 our mass at the time. The collision was catastrophic for both systems. But the Milky Way won. We absorbed Enceladus completely, consuming it like a python swallowing prey. Its stars now populate our halo, billions of them orbiting where they were never supposed to be. The Gaia spacecraft detected this ancient crime by studying how stars move. Stars from Enceladus orbit differently than native Milky Way stars. They move in retrograde directions, backwards compared to our normal rotation. Their paths are tilted and eccentric. Their motion betrays their foreign origin, even after 10 billion years. Chemical analysis confirms the story. These stars have different elemental compositions than native stars, less heavy metals, different abundance patterns. They formed in a different galaxy with a different chemical history. Now they orbit here, captured and assimilated into our structure. The Kraken merger, an even more massive ancient collision. Before Gaia Enceladus, there was Kraken. About 11 billion years ago, an even more massive collision reshaped our galaxy completely. Kraken might have been half the Milky Way's mass at that early time, making it the largest merger event in our history. This collision triggered intense star formation, building much of our current disk structure. The violence was unimaginable. Two galaxies interpenetrating, tidal forces ripping both apart, gas clouds compressing and forming millions of new stars simultaneously. Kraken's remains are harder to identify because they mixed so thoroughly into our structure over billions of years. But they are there. Billions of stars that once belonged to something else. Computer simulations reconstructed the collision based on stellar orbits and chemical signatures. The models show devastation on a galactic scale, and it happened so long ago that most evidence has been erased by time and subsequent evolution. Stellar stream fossils. Every river marks a massacre. Look at any map of stellar streams around the Milky Way and you are looking at a graveyard. Each stream represents a galaxy that wandered too close and paid with its existence. The Helmi streams, Sequoia Dwarf, various unnamed ribbons of stars circling through our halo. Every one is a fossil, evidence of ancient meals, victims of our gravitational appetite. These streams will orbit for billions of years before dispersing completely. Temporary monuments to galaxies that no longer exist. The streams tell stories of violence if you know how to read them. Their shapes reveal how the dwarf galaxy was torn apart. Wide streams come from larger victims. Thin streams mark smaller prey. Multiple wraps around the galaxy show repeated orbits before final dissolution. Each stream is unique, each death different, but the outcome always the same. The Milky Way grows larger while its victims scatter into history. The perpetual growth machine, rich gets richer. Galactic cannibalism explains why big galaxies keep growing while small ones disappear. The process is self-reinforcing. Once you become massive enough, your gravity reaches farther. You capture more victims. Each meal makes you larger, which extends your gravitational reach even more. You capture more victims. Positive feedback. Runaway growth. The rich literally get richer in galactic evolution. Dwarf galaxies live on borrowed time. They orbit giant galaxies like prey animals near predators, constantly threatened. Most eventually get eaten. Only a few survive in isolation, far from any large neighbor. The Milky Way dominated the local group through systematic consumption. We built an empire by eating everything within reach. And we are still eating, still growing, still adding to our collection of stolen stars. Here is the disturbing truth most people never consider. Those devoured galaxies are not gone. Their stars still exist, still shine, still orbit. They just orbit us now instead of their original centers. The Milky Way is not a single coherent entity. It is a collective graveyard, an empire built from the corpses of dozens of smaller galaxies. You might be made of elements forged in a star that once belonged to Gaia Enceladus. Those atoms cycled through the galaxy, eventually coalescing into our solar system, into Earth, into you. We are all immigrants in a sense. citizens of an empire that erased borders by consuming neighbors. The Milky Way grew big through violence, through mergers, through unrelenting cannibalism, for trillion solar masses did not appear from nothing. We stole it, one galaxy at a time, over billions of years, and the process continues. Sagittarius is dying right now. The Magellanic Clouds will be next. Andromeda will be the final meal, the merger that transforms us completely. Galactic cannibalism never stops. It is written into the mathematics of gravity. The strong devour the weak, the massive consume the small, and the Milky Way has been feasting for over 10 billion years. Part 5, Scientific Revolution and the Universe Rewritten. 400 billion stars, doubling our chances of finding life. The star count just doubled. The Milky Way contains approximately 400 billion stars, maybe more. 400 billion chances for planets, for life, for civilization. If you counted one star per second, it would take 12,700 years to count them all. Old estimates said 200 billion. They were completely wrong. Double the radius, and you increase volume by a factor of 8. Most newly discovered stars are red dwarfs, small and dim but incredibly common. They hide in plain sight, invisible to casual observation. 400 billion stars means 240 billion potential planetary systems. Conservative estimates suggest 2.4 billion habitable worlds in our galaxy alone, just doubled from previous calculations. Even if life is rare, 1 in a million habitable planets, that still leaves 2,400 worlds with biology in the Milky Way. The probability of finding alien intelligence just increased dramatically. More stars means more chances. The search for extraterrestrial life became twice as promising overnight. Every galaxy was measured wrong. The universal mistake. The Milky Way is not special. If we got our galaxy wrong, we got all galaxies wrong. Researchers tested nearby spirals using new measurement techniques. Every single galaxy came back larger. Andromeda grew from 220,000 light-years to 300,000. Triangulum doubled from 60,000 to 100,000. The pattern was universal. We systematically underestimated every spiral galaxy in the universe. This affects everything: collision rates, galaxy evolution models, cosmological calculations. The cosmic census needs complete rewriting. James Webb changed everything. The James Webb Space Telescope forced astronomy to admit its mistake. Webb sees through dust, revealing hidden structure everywhere. It tracked stellar streams at impossible distances, measured dark matter through gravitational lensing with unprecedented precision. The result was undeniable. For trillion solar masses, triple the old estimates. Scientists could not argue with direct measurements from the most advanced telescope ever built. Conferences erupted in debate. Slowly, grudgingly, the consensus shifted. The textbooks were wrong. The boundary problem and our cosmic future. Where does the Milky Way actually end? Nowhere. There is no edge, just gradual fading into darkness. Star density drops smoothly from center to periphery. Dark matter extends even farther, possibly 400,000 light-years or more. The galaxy has no border because the universe is continuous. 200,000 light-years is our best answer today, using the virial radius. But that number will change as technology improves. It always does. The Milky Way is enormous, twice as large as we thought. 400 billion stars orbiting in a dark matter halo. A gravitational empire built from devoured galaxies. A cosmic neighborhood headed for collision with Andromeda. We spent 70 years teaching the wrong size in every classroom. Now we know better. The galaxy revealed its secrets reluctantly, forced by technology to show its true scale. This discovery changes everything. When Andromeda hits us, how many stars exist where life might hide? The search for alien intelligence, our understanding of dark matter and dark energy. Every calculation built on the old measurement needs revision. And if we got our own galaxy this wrong, what else have we miscalculated? The measurement continues. The discoveries keep coming, and the Milky Way keeps teaching us that we know far less than we think about the place we call home. Welcome to the real Milky Way. Twice the size, twice the mystery, and twice as many chances we are not alone.